Hello, so far we've seen 3 different videos about the Fourier series, which is a lot of information, but it's sort of a complicated topic, so it's, I think, useful to take things a little bit slowly. So in the last video, we defined a Fourier series which is associated with a function, and we determined how to find how to define the coefficients of that series. So let's write that definition down again. So let's do blue, yep. For a function f of x, so let's see, let's let f of x be piecewise continuous on an interval from negative L to L. Then we will define the Fourier series as a function, or as a trigonometric series, which is associated with f of x. So it's not exactly equal to at this point. That's not what we want to say. But we're going to associate it with the series a0 over 2. And then we'll do an infinite sum, n equals 1 to infinity. We have a cosine term and a sine term. So in our heat equation and wave equation problems from the last section, we saw that it was really useful to have things written in terms of sines, but sometimes it's going to also be useful to have things in terms of cosines, and so that's why we end up needing both here. And our coefficients are given by these formulas. So the AN are given by these integrals with cosines, negative L to L, f of x times our cosine n pi x over L dx. And that's for n starting at 0 because it includes a0. And for bn, there's no 0 sine term, but otherwise it's the same. Negative L to L f of x, except with sine n pi x over L dx. And that's for n equals 1, 2, etc. All right, so that is our definition. And what we're going to do in this video is do one example, although there are a couple of other examples in the book that will be useful for you to read through for your homework, and I'll probably end up doing one in Zoom. And then we're also going to just sort of list through some of the properties of the Fourier series for our reference, although we won't go deep into the theory of it. Alrighty. So here's an example. So this is example 4 in the section. And we're just going to compute the Fourier series for a given function. So here's our function. We need it to be piecewise continuous, and it is. So it's going to be negative 1 from a negative pi to 0, and 1 from 0 to pi. So what we note here is that L is going to equal pi, and that's going to make some of our computations a little bit simpler, because instead of n pi x over L, we just get nx. Let's see. Okay. Now, all we have to do is compute our coefficients, and we have our formulas up here. So let's think about the AN first. Actually, let's draw our function just so that we have a good grip on it. So we're going to go from negative pi, that's a negative pi, to pi, and then negative 1 and 1. And we're going to have, we don't really care what's happening at the endpoints because they don't matter to us. They don't matter to us. When we integrate and everything, they just don't matter. So something we could observe here is that this is an odd function. Remember what that means, that if we rotate this around the origin, it's the same thing. That points we have up here are the same down here. And so now let's compute our coefficients. So our an is going to be 1 over pi, right? Oops, here's a mistake right here. That should be an L up there. All right, so our L is pi, and so we have 1 over pi, integral from negative pi to pi of, let's leave it as f of x cosine n pi x over L is going to be nx dx, okay? Now, an observation here is that this is an even function, and this is an odd function. And so the combination of them, the product of them, is also an odd function. And so if we look at this example over here of an odd function, and if we were to integrate this from negative pi to pi, we get the same thing down below in negative as we have up in the positive. And if we integrate over all of that, it cancels out and equals 0. So just like we saw in a couple of videos ago, any integral of an odd function from negative L to L is going to be 0. And so that means that the fact that the integrand here is odd implies that this equals 0 for any n. So good, that's easy. I forgot to point out that the fact that the product of an odd function with an even function, that results in an odd function, that's a homework problem. So think about that some more for your homework. Next, we will compute our Bn coefficients. So we get 1 over pi, negative pi to pi, f of x sine nx dx. And we can think about our evenness and oddness again. So this is odd, and this is odd. And the product of these is, in fact, even, and that's also in the homework. And so what do we know about an even function when we integrate it from negative L to L? Well, it's just twice what you get if you integrate from 0 to L. So this is going to equal 2 over pi, integral from 0 to pi of f of x sine nx dx. And that makes it easier because we know what f of x equals from 0 to pi. Then it's always 1. So we can come down here and we get 2 over pi, integral from 0 to pi of sine nx dx. This we can just integrate because we know how to integrate, and we get a negative 2 over pi n cosine nx evaluated from 0 to pi, which is -2/pi(n). So cosine of n pi is either 1 or -1, depending on whether n is even or odd, right? So if it's odd, it's -1. And if it's even, it's +1. And so the way we can express that is -1 to the n. Okay, so this is cosine of nx. Or, sorry, not nx, of n pi. And then we will subtract cosine of 0, which is 1. That should be a big parenthesis there. And so we can simplify this just a smidge and sort of cancel out that negative sign, and we get 2/n pi 1 minus -1 to the n, okay? And we can think about what this equals. Let's write it down here. If n is even, then the 1 minus 1 is going to cancel out. So that's 0 if n is even. And if n is odd, then we get 1 minus -1, which is 2. And so then we get 4/pi(n). N is odd. Okay, so that's what our bn's look like. Now we can sort of put this all together and get our answer. So the Fourier series associated with f of x, we can pull out this 2/pi and write a general term with an infinite sum. So we have this plus this is our bn from up there. And then we can also write it out with a few of the terms. So we get 4/pi times, first term is just sine x plus 1/3 sine 3x plus 1/5 sine 5x, etc. So this is sort of an extremely weird thing that we've just done. We've taken a function that just was -1 or 1, and we've turned it into a bunch of sine functions. So why do we do this? Well, this figure from the book shows what some of the partial sums of this Fourier series look like. So the dotted line here is the first two terms. So that means that it's just going to be 4/pi sine x plus 4/3pi sine 3x. So with an infinite series, you think of in terms of partial sums. So you add up the first 2 and then the 3 and then 4 and 5 and 6. And as you add in more and more terms, that should hopefully converge to something. And the more terms you add, of course, the closer that you get to having the whole infinite series. So if we just take the first 2 terms, that's kind of a really rough estimate, but 9 terms should be a little bit better to adding up the whole thing. And then you also could imagine doing the first one, which would just be a sine function. And so that might look something like this, right? So this would be one term. And if you just take one term, that's a really bad estimate of what our function f, the blue line down here, actually looks like. Okay, our -1 and 1 step function. It doesn't look anything like a sine function. But now if you add two terms and you get the dotted line, you get this dotted line here, well now that is looking a little bit better. And if you look at 9 terms and look at the solid one here that I'm doing in green, now it's still a sine function, it's still wavy, but it's showing you this jump that you have, and it's starting to get flat. So you can imagine if you plotted this out for a lot of terms, it might actually sort of look like the function that you're trying to approximate. The other thing I'm going to point out is that our function f is not periodic, and in fact it's only defined from -pi to pi. But the Fourier series is periodic, which it's going to be because it's just the sum of sines and cosines. And so the Fourier series is always a periodic function, which is going to be sort of an important observation. All right, so now I'm going to talk about so we talked about whether, we've been talking about this in the sense of the Fourier series approximating our function, but we have no idea if this infinite series even does converge to anything. So now I'm going to tell you when it does. So let's talk about some theorems about the Fourier series. Okay, theorem. If f and f prime are piecewise continuous on -L to L, then for any x in that interval, though maybe not at the endpoints, we don't care about the endpoints, we get that our Fourier series, AO over 2 plus n equals 1 to infinity and cosine at pi x over L plus bn, oops, that's hideous, sine n pi x over L. This is going to converge. So now we've taken a particular x and plugged it in. And so this is just an infinite sequence of numbers, or it's an infinite series of numbers. And we can talk about whether it converges or not. So it might be infinity, or it might be a number. And this theorem is stating that it is a number, a finite number. It converges to, so this is going to be some new notation, f of x plus f of x minus. So what does that mean? These are our left and right hand limits. So we can write it this way. F of x plus is the limit as h approaches 0 from the right of f of x plus h, and f of x minus is the limit as h approaches 0 from the left of f of x minus h. So let's draw a function, an example of a function. Let's see. Okay, let's draw a couple of examples here. So let's say we have x1 and x2, and This is y1 y2 and y3. Doesn't really matter. So let's talk about the values at x2. So f of x2 minus, in this case, so is going to be where our f is heading as we go from the left. And so if we're looking at what the function's doing as we approach x2 from the left, we're getting up to y3. And then f of x2 from the right is going to be where we're heading from the right, and so that's going to be y2. And so that really matters when you have this discontinuity, because where your function's going from one side is different from where it's going from the other side. On the other hand, if you are continuous at this certain point, then let's see, f of x1 from the left is going to be the same thing as f of x1 from the right. From the left, you're going to the same place as you are from the right, and that's going to be y1. So that means that this thing, this value over here, equals f of x if f is continuous at x. And so that this Fourier series converges exactly to your value f of x wherever f is continuous, and it converges to the average value of the left and right hand limits if you have a discontinuity. So this right here would be 1/2 f of x2 minus plus f of x2 plus. Okay. So the point is that for the most part, this thing converges to our to the function that we want it to, except for where we have a discontinuity, and then it converges to the average value between the discontinuities. So let's think about the example that we just did. And this is going to be example 6 in the section. And it's asking to which function does the Fourier series for f of x equals -1 and 1, negative pi to 0 and 0 to pi. So to which function does the Fourier series for this converge? So the theorem tells us that the Fourier series will converge to f exactly wherever f is continuous. So let's see. For x in between negative pi and 0 and 0 and pi, for x in there, the Fourier series will converge to f of x. Okay? Now for x equals 0, the Fourier series will converge to 1/2 f of 0 minus plus f of 0 plus. Now, what does f look like? it's this, right? And so f of 0 minus is going to be -1. And f of 0 plus is going to be 1. And so the average of those two values of -1 and 1 is just 0. Now I forgot to state the last part of this theorem, but it's in the book, and I'll sort of write it here. So that tells you what happens at the endpoints. So for x equals pi, that's our endpoint, the Fourier series will converge to the average of the right-hand limit of -pi and the left-hand limit of +pi. So this is pi and -pi. Let's make a smidge more room. And so the right-hand limit of -pi is going to go to -1, and the right-hand limit +pi is 1. So we get the same thing here, equals 0. And this is actually true for both endpoints, positive and -pi. So now I'm going to erase this graph so I can draw another one. And now what I'm going to draw is the function to which our Fourier series is going to converge. Okay. So we sort of know what's happening between -pi and pi. -1 and +1. So it's going to look just like our f here. And then we also know that at these discontinuities, we're going to get this average value. And then furthermore, we know that the Fourier series is periodic. So we can, and it's defined on all values of x, so we can spread this out for the rest of the domain. 2pi, 3pi, -2pi. And we'll end up just repeating the same thing over and over, and we'll get our midpoint values over here. And of course, that is based on the figure that we had before. That looks sort of exactly what we would have expected, including these values, these sort of center point values here, because our sine waves, if we're going to jump, we're going to have to jump from one to the other, and they're probably going to meet right in the middle. So that really is very intuitive. All right, this video is starting to get pretty long, but I'm glad I did that example. So I'm going to sort of skip some of the rest of the stuff, and I'll let you read it in the book. I'll just say it really briefly. So other properties that we get from Fourier series under certain conditions are uniform convergence. So what we just talked about was pointwise convergence. We talked about at a single x value what that series would converge to. Uniform convergence is a much stronger property that talks about sort of how a function converges for all x's at like kind of the same time. But that's very much out of the scope of this class, but it's an important concept if you're going on to do more analysis. differentiation. So you can, under certain conditions, you can differentiate the Fourier series termwise. I spelled that wrong. Whatever. And then similarly, integration. You can integrate termwise, just like we had with power series. And so those are really nice properties, because if we have this infinite sum and we know that we can integrate and differentiate it term by term, those terms are really easy to integrate and differentiate. They're just sines and cosines. So that's sort of that's it for Fourier series, except for how it's not. In our next section, we're going to talk about breaking these down into just sine and cosine series when we need to. Oops.